Hi, in this video we will conduct instruction fine-tuning of a Llama 2 model using parameter-efficient fine-tuning, PEFT, quantization, and low-rank adaptation, LoRa. The use case is to do instruction fine-tuning of an LLM for a specific downstream task. So after the release of proprietary LLMs such as GPT 3.5 or ChatGPT and also GPT-4, the open source community also came up with powerful models, but they came with downsides. Many open source models had restricted licenses for use for research purposes only, plus only large organizations could afford to fine-tune or train LLMs. The Llama 2 series of models aims at exactly addressing these issues. They come with a commercial license and some new methodologies that allow to fine-tune on consumer GPUs with limited memory. In this notebook, we will fine-tune a Llama 2 model with 7 billion parameters here on Google Colab. And in general, the Google Colab has limited memory. For example, the T4 GPU has only 16 gigabytes of VRAM, which is barely enough to store Llama 2 7B model's weights. This makes full fine-tuning quite impossible, and that is why we need to use parameter-efficient fine-tuning, otherwise known as PEFT, especially its technique called low-rank adaptation. By doing this, we will reduce the large weights matrix into smaller low-rank matrices, allowing to freeze the pre-trained model's weights and train only a small number of model parameters. This means we can have multiple lightweight portable LoRa models for various downstream tasks built on top of the pre-trained model. In this notebook, we will use the QLoRA technique to fine-tune the model in 4-bit precision. So when a base model is pre-trained, it can predict the next token in a sequence. This is not very useful, and we need to conduct instruction tuning to align the large language model answers with human expectations. And there are two main techniques. The first one is supervised fine-tuning, when we do fine-tuning on a data set of instructions and responses. The second technique is reinforcement learning from human feedback, or RLHF, when models are fine-tuned to maximize a certain reward signal, for example, using the proximal policy optimization methodology. And this signal is derived from human evaluations of model outputs. In our case, we will perform supervised fine-tuning. Now, let's run some code to prepare for the fine-tuning. So I have already run these two cells. So the dependencies are installed. They include such libraries as accelerate, PEFT, bits and bytes, transformers, and TRL. I have also logged into the Hugging Face Hub, which is required to be able to download models and to upload the fine-tuned model. Now let's run the import statements, and while they're being run, a few words about the data itself. So for the fine-tuning to be efficient, the quality of the instruction dataset is essential. For example, the Llama paper, and Llama stands for less is more for alignment, it showed how one can efficiently fine-tune a model on just 1,000 high-quality examples. The size of the LLM is also fundamental to leverage the pre-existing knowledge. There are several efficient formats for the instruction dataset. For example, the Llama 2 template or the Alpaca or Vicuna formats. In this example, we will reformat our instruction dataset to follow the Alpaca template. And please note that you don't really need to follow a specific prompt template if you're using the base model for fine-tuning instead of the chat model. So there are several ways to come up with instruction dataset. They include, for example, using an existing dataset and convert it into an instruction dataset, for example, the FLAN dataset. We can also use existing large language models to create synthetic instruction datasets. For example, the Alpaca dataset generated using the DaVinci GPT-3 model. Or we can use human annotation, and create instruction dataset with such an example as, for example, the Dolly dataset generated by thousands of Databricks employees. All three datasets are available on Hugging Face. Each of the methods has its own advantages and disadvantages and depends on the budget, time, and quality requirements. So in our case, we are going to use the Alpaca GPT-4 dataset, which has the same prompts as the Alpaca dataset, but the responses were generated by the much more superior GPT-4 model. It is available at Hugging Face Hub, but we will demonstrate how it is possible to build an instruction dataset completely from scratch using just a raw JSON file. We will download the JSON file and create a Hugging Face dataset from it. So let's run the download script. The length of the dataset is 52,000 examples, and it looks like this. Each example is a dictionary. It has the instruction field, the input field, and the output field. And not all examples have the input field, so we'll have to deal with it later. Now let's sample 1,000 examples in a reproducible manner, because fine-tuning on all 50,000 examples would take too much time. That we'll save the JSON file, and using this cell, we will load the raw JSON file into a Hugging Face dataset object. Next, we will work on the functions that reformat the dataset into the acceptable format. The first function is build prompt with input, and it deals with a situation when an example has all the three fields: instruction, input, and output. Then we have a function that deals with the case when there is no input, just instruction and output. And finally, the main function, formatting func, which decides which of the previous two functions to use, the one with the input or the one without the input. And just to demonstrate how this works, let's print a random instruction response pair. So here's the instruction. The input was added to the instruction, and here's the response. Now let's see another example. In this case, the response has more lines, and the response is more structured because it has these numbers for each of the lines. Lines are numbered. As an example, we can have a look at the Dolly dataset, which was generated by thousands of Databricks employees. We can load it directly from the Hugging Face Hub. And we can have a look at it. So it also has instruction and response pairs, another random pair, and another one. So for our purposes, we will use the Alpaca GPT-4 dataset. Now let's free up some memory. And now comes the part where we prepare for the fine-tuning job. First of all, this is our base model. It's the model that will be fine-tuned. It's Llama 2 7B. It's a base model, not a chat model. Next is the name of the model that will be fine-tuned. We will call it Llama 2 7B Alpaca GPT-4. Next comes the quantization parameters, and we're using bits and bytes config class, which is which is part of the transformers library, and it sets up the quantization parameters. Quantization is a process that reduces the precision of the model's weights, which can significantly decrease the model size and inference time, but with a potential trade-off in accuracy. This class has several parameters. The first one is load and forbit. Basically, this parameter enables loading of the model weights in 4-bit precision, and this reduces the model's memory footprint. The next parameter is BNB 4-bit compute type. It specifies the data type for computation after quantization. And here the computations will be performed using 16-bit floating point numbers. This choice balances between computational efficiency and maintaining sufficient precision. And finally, the last parameter is BNB 4-bit quant type, which defines the type of quantization to be applied. NF4 stands for 4-bit normal flow quantization. It's a custom data type that exploits the property of the normal distribution of model weights and distributing an equal number of weights per block to each quantization bin. This lets us enhance the information density. Next, we will load the model using the auto model for causal LM, which is a class that loads a pre-trained causal language model. It's a type of language model that predicts the probability of a word based on preceding words. We will use the quantization config parameters set up for the model for 4-bit quantization. Then we will load the tokenizer using the auto tokenizer class. It has the trust remote code parameter. Basically, this parameter allows the execution of custom code not covered by the standard tokenizer. It may be a security risk if you don't trust the source of the model. The add special tokens method updates the tokenizer's vocabulary. In this case, it sets the padding token to pad. And padding tokens are used to ensure that all sequences in a batch have the same length, which is necessary for efficient processing of batches. So let's run this code. While it is being run and the model is being loaded, let's review the next low rank adaptation parameters. For this, we will use the LoRa config class that defines the configuration for applying low rank adaptation to a model. And this is part of the parameter efficient fine-tuning, or PEFT. PEFT works by only updating a small subset of the model parameters, making it much more efficient. So we are using the following parameters and methods for the LoRa config class. R, which stands for LoRa attention dimension, or the rank of the adaptation matrices. The lower the rank, the fewer parameters are added, which controls the model's complexity and the amount of computations. Here, R equals 8, which indicates a relatively low rank adaptation. Target modules are the names of the modules to apply the adapter to using LoRa. These modules typically include projection layers within the transformer architecture, such as, in our case, query projection, key projection, value projection, and output projection, as well as some custom modules, gate, up and down projections. Adapting these layers allows the model to modify its attention mechanism and output processing in a task-specific manner. The next parameter is bias, which signifies bias type for LoRa. None here means that the biases will not be updated as part of the LoRa process. And the last parameter is task type, which is causal LM, indicates that the adaptation will be done for the causal language model task. The add adapter method modifies the model based on the LoRa configuration. It inserts low rank matrices into the specified target modules, which we have reviewed here. And this allows these parts of the model to adapt to the new task with minimal additional parameters. So the model is still being loaded. Takes some time. Now it's the shards, and the process will soon be over. It's over. So let's run the LoRa config part. It's pretty straightforward. And next, we will train some training hyperparameters for our model. These include the output directory, which will be the directory where the model artifacts will be saved. Per device trained batch size means the batch size per GPU for training. The smaller the batch size smaller batch sizes are used to fit the model into limited GPU memory, while a larger batch size can speed up training. And in our case, it's pretty small. It's 4. So gradient accumulation steps is the number of steps required to accumulate the gradients during the update process. Next is the optimizer. It's Atom, 32 bits in our case. Then is the number of steps after which we save the checkpoint of the model. So here we save a model checkpoint every 10 steps. We also log everything every 10 steps. The learning rate is the initial learning rate, and it's a pretty common number as a starting point for fine-tuning large language models, 2e-4. Max grad norm is gradient clipping to prevent exploding gradients. Max steps means the total number of training steps, which will be 1000 in our case. Warm-up ratio is the ratio of steps for a linear warm-up in the beginning of training. And the learning rate scheduler is constant in our case, which means the learning rate will not change. We have 2 additional hyperparameters. They are gradient checkpointing, which enables saving memory at the expense of slower backward pass, and also push to hub. The model will be pushed to Hugging Face hub every time it is saved. We will also use the SFT trainer class, whose backend is powered by Accelerate, and this allows to easily adapt the training to our hardware. For example, if we have 2 GPUs, then we can run this command, and we will be able to perform distributed data parallel training. So first let's run the training arguments, and now let's set the SFT trainer, which is, if you remember, supervised fine-tuning. So we initialize the class for SFT trainer. It's a specialized trainer for supervised fine-tuning of pre-trained language models on a specific data set. We will use the TRL library for this. TRL stands for Transformer Reinforcement Learning. And SFT trainer has the following parameters. First, it's the model, the pre-trained language model for causal language modeling, potentially with the modifications such as quantization and adapters for low-rank adaptation, LoRa, as we did before. The model is ready to be fine-tuned on a specific task or a specific data set. Then we have the training arguments, which we have just reviewed. Then the training data set, in our case, it's the Alpaca GPT-4. Packing here stands for indicating whether the trainer uses data packing. It's an efficient method to utilize available token space in each batch to reduce padding and improve training efficiency. Then we indicate the tokenizer. The maximum sequence length is the maximum sequence length that the model will accept. Inputs that are longer than this will be truncated. And finally is the formatting function, which we have reviewed before. It used to format the dataset examples into a structure that is suitable for our training. Next, well, first let's run this cell. Now the model is ready for fine-tuning, and we will run trainer train, which will actually set off the fine-tuning cycle. In our case, it will last for 2 hours, It'll have 1000 steps, and it will fine-tune the base Llama 2 7B model using 1000 examples of pairs of instructions and responses. Now the fine-tuning process is over. The model has been fine-tuned for about 2 hours for 1000 steps, about 80 epochs. As you can see, the training loss has been gradually decreasing. The model was also pushed to Hugging Face Hub, and if we go there, we can see that the model is in the hub. It's possible to download the model in the same way as any other model. There is a brief model card. Model files are in this repository, and we can also see the training metrics using TensorBoard. Where besides different hyperparameters such as epoch learning rate, we can also see a plot for training loss, and it's the same picture. It's been gradually decreasing except for this small bump. So now that the model is fine-tuned, we can save the model and the tokenizer locally, and then we can test the model. So I have already run this part of the code in the interest of time, because it also takes some time to do this. Basically, we load the newly fine-tuned model from the Hugging Face Hub, just in the same way as any other model from the hub. We load the same tokenizer. We use the same quantization config parameters, the same auto model for causal LM. And then we test the model using an example prompt. So in this case, the instruction is explain the differences between Mars and Venus. And this is the model's output after the adaptation, after the low rank fine-tuning. This is the prompt instruction, and this is the response. As you can see, the response is very structured. So it looks like the model was aligned successfully because it explains different aspects of the differences between the two planets. It's the area in mass, it's the atmosphere, and the climate with all these different details. And next, we can test the same prompt, but we disable the adapters. So this is as if the model has never been fine-tuned. This is the base model, Llama 2 7B base model, before any fine-tuning. And as you can see, the output to the same instruction, the response is not as structured. So apparently, the model is trying to answer the question, but it's not done in the same way as the structured output of the fine-tuned aligned model. And in the end, you can find a list of references which were used to compose this notebook, and they contain the main reference with some information about the model used that was fine-tuned in that case, dataset, and even some code, including some Google Colab code. So if you're interested, please have a look at those.